we're going to take a look at carbohydrates in this chapter, and looking at just the word carbohydrate itself. We're going to see some carbons and some waters is where the early name came from. So lines of carbons and then a bunch of H's and OH's. So this chapter is the beginning of our biomolecules, and they are going to just basically take the organic compounds and chemistry that we've done and put them into slightly bigger molecules. You can see there's huge carbon-based molecules all over the place here. So we're going to work on those. We're going to see some functional groups still. A couple of these should be familiar, or at least should be familiar if you think about it a bit. Aldose and ketose. You can maybe guess which functional groups those are. So an aldehyde and a ketone. Pentose. Pent was our prefix for 5, and hexose our prefix for 6, and so these are going to be 5 carbon sugars and 6 carbon sugars. And you can see a frequent suffix for all of our sugars is ose, like you might be familiar with glucose, and so we see ose on all of these because they're related to sugars. Another thing that we've seen before that we're going to see with our carbohydrates is chiral centers, and so those were our carbons with 4 unique groups attached to them. And then some later things that we'll get to, a new functional group called a hemiacetal, and within those hemiacetals we'll also be looking for some anomeric carbons, but that will be a little bit lower down. So first of all, we're going to look at monosaccharides, which are going to have these single lines or a single ring. And so those are single sugars is what we're going to be looking at. As we look at some of these, D-glucose is what we would call our blood sugar. A couple things we can look at on D-glucose. So first of all, if you look at the top functional group here, and we can look at some of those as we go across all the way here. Notice it's not here, but then we suddenly have this carbonyl here that jumps out at us. Here's another carbonyl and another carbonyl. So as I look at these, on the D-glucose, this is a carbonyl at the end of a chain, and so this I would say is an aldose or an aldehyde. So D-glucose is an aldose sugar. We could also count the number of carbons. 1, 2, 3, 4, 5, 6. Some of them were numbered for you. And so D-glucose we could also say is a hexose sugar. This is just to make connections. This is our blood sugar when we talk about blood sugar levels. And another term for this is dextrose. And that dex comes from this D. This D actually stands for dextro, and it relates to the way that the light is rotated when you shine it through a solution of glucose. And so dextrose is the same as glucose. For whatever reason, they put this on nutrition labels a lot. I don't know if it's to make you think that it's something other than sugar or what, but that is D-glucose. And you can see with a mirror here that L-glucose is the exact reflection of that D-glucose. And so those two are enantiomers, like we learned back in chapter 12. For the D-glucose, if I look at my 5th carbon here, the OH is on the right side, and when I look at the 5th carbon for L, the OH is on the left side. So that's where the D and the L prefixes come in, is looking at those bottom hydroxyl groups. I won't test you on that, but it's just worth observing. Looking at fructose here then, you can notice here that this is a ketone, right? Because it's a carbonyl in between 2 other carbons. So I could say that this is a ketose sugar, and maybe over here would have been better to say that this is an aldehyde instead of an aldose. If I count the carbons, 1, 2, 3, 4, 5, 6, again I have a hexose. This is fruit sugar, and it tastes sweeter than glucose. So we'll say it tastes extra sweet, which is why they, excuse me, take corn sugar, which is about 50-50 glucose and fructose, and they hit it with some enzymes that convert some of the glucose into fructose, and then the result is you get high fructose corn syrup. So it's more fructose than the normal 50-50 division, and that makes it taste extra sweet, which makes it good for putting in sodas and all kinds of different processed foods. So high fructose corn syrup, the fructose helps it taste extra sweet. We can continue through here. Looking at the ribose, I'll let you figure out what kind of functional group we have and how many carbons. We find this in RNA's backbone. And in DNA, it's deoxyribose, and so one of these hydroxyl groups is removed, and we'll see more about that in chapter 17. So that's a little introduction to some of these vocabulary words. The last thing I want to look at with you in terms of introduction is these chiral centers. We worked on these a little bit in chapter 12. So let's just pick out one of these carbons on the glucose. And if you think about the groups attached to it, here would be one group, and the O, or the H, and the OH, and then this other big group here. And so carbon 2 there is a chiral center. And you can work your way down all 6 of these, and you would find that these middle 4 were also chiral centers. Down here at the bottom, this carbon's attached to 2 hydrogens, so that can't be a chiral center because it's got a duplicate. And up here, this carbon is only attached to 3 different groups, so it also can't be chiral. So in glucose, I have 4 chiral centers. It's definitely a chiral molecule. And incidentally, our bodies can only metabolize, and everything's fit for these D-glucose molecules. L-glucose can't be digested, can't be used at all in your body. And so we need this dextro version of glucose to work in our body. So it matters what enantiomer you have. This is a good example of one that's biologically useful and one that is not. They actually tried using L-glucose as a sugar sweetener, a sugar replacement, and it just is too expensive to make, so that's why they don't use it instead of aspartame or some of those other sugar replacements. So some background on our sugars, on our monosaccharides. Next up, we'll look at some structures and some reactions.